so we were doing the Faulkner-Scan solution last time. So we're going to continue that now. And just to remind you, this is kind of like a more generalized version of the Blasius solution, except for now we're taking into account the pressure gradient term. And so we're substituting in all of our derivatives of the stream function in here. And we ended up with this equation. And let me just make sure that all this looks good. So we divided through by UE, right? Yes. Okay. UE U prime F squared. Theta. Yes. Minus UE U prime F prime minus F prime squared. Okay. So I actually, okay, this is fine. This is fine. Okay, so what we're gonna do is, wait a second. Where is the, oh wait, okay. Yes. UE. Okay, so what I'm gonna do is I'm going to do one sort of manipulation here. So I'm going to rewrite this term as the following. So I can write this as UE divided by L times the X derivative of UEL F double prime. And then I get back those two terms when I do the product rule. Okay, so I have now UE prime F prime squared minus UE over L ddx of UE times L F double prime is equal to UE prime plus nu over L squared F triple prime. Okay, so I ideally would like to have the highest order derivative with a leading coefficient of 1. And then I'm going to rearrange these terms so that I have 1 times F triple prime plus like the descending derivatives after that. Okay, so I am going to multiply by L squared over nu. Like so. And when I do that, and then I'm gonna rearrange. Okay, so when I do that, I will get F triple prime plus L squared over nu times UE prime plus L squared UE over L times nu ddx of UE times L F double prime minus L squared over nu UE prime F prime quantity squared is equal to 0. Hang on. I'm also going to combine these two terms together. So I have F triple prime plus L UE over nu ddx of UE times L F double prime plus this lumped term. So I have L squared over nu times UE prime, quantity 1 minus F prime squared. Is equal to 0. And I am going to call the seventh term and second term supposed to be a double prime. Or did we get a third prime from somewhere? Oh, no, this should be a double prime. Thank you. I realized that I wrote this wrong. This should be 1 over L. Sorry. There. Sorry about that. Okay, so I am going to lump this factor out front. And I'm going to call this lambda. And I am going to lump, oh no, not that. That's bad. That's worse. There we go. That's good. Okay, and then this factor out front is going to be called gamma. Okay, so what we have left is we have F triple prime plus lambda times F double prime plus gamma 1 minus F prime quantity squared is equal to 0. Deeply nonlinear function. All right. And so the thing is, if we want to have a function f, which is what this ODE is acting on, if we want it to only be a function of eta and independent of x, that means that lambda and gamma must both be constants. So in order for f of eta to not depend on x, then lambda and gamma must both be constants. So what that means is that lambda, which equals L over nu times ddx UE times L, is a constant. And gamma, which is equal to L squared over nu due dx, is also a constant. All right, so our governing equation plus boundary conditions, which is also called the Faulkner-Scan equation, is the following. So we have F triple prime plus lambda F double prime plus gamma 1 minus F prime quantity squared is equal to 0. So it's just the same thing I wrote before. And then our boundary conditions are eta, sorry, F at eta equals 0 is 0. And F prime at eta equals 0 is equal to 0. And then F prime as eta goes to infinity is equal to 1. This can only be solved numerically. All right. And so our job now is to figure out UE of X and L of X. So we'd like to understand UE of X and L of X. All right. So we have that gamma is equal to L squared over nu times UE prime, which I can rewrite as L squared UE prime is equal to gamma times nu. And we also have that lambda is equal to L over nu times d dx of UE times L. And I'm going to just expand this out. So I have that lambda times gamma is equal to L quantity UE prime times L plus UE L prime. All right, so we have lambda times nu is equal to L squared UE prime plus UE L prime L. And I'm going to call this star star, and I'll call this one star. So if we take 2 times star star and then subtract star, we get the following. So we have two lambda nu is equal to 2 L squared UE prime plus 2 UE L prime L minus L squared U. Actually, let me rewrite this a little bit. So gamma nu is equal to L squared U E prime. So we have nu times the quantity 2 lambda minus gamma is equal to L squared U E prime plus 2 U E L prime L. And I'm going to rewrite the second term slightly. So I have nu times 2 lambda minus gamma is equal to L squared U E prime. And then I'm going to rewrite this as UE times d dx of L prime squared. Sorry, this is not the prime yet. L squared. And then we can notice that the right-hand side as written can be rewritten as a product rule, like doing the product rule in reverse again. So we have nu times 2 lambda minus gamma is equal to d dx of ue L squared. Okay. So I can separate variables and integrate this. So I have nu times 2 lambda minus gamma dx is equal to the differential of UEL squared. Since we said lambda and gamma were constants, and we also know that the viscosity is a constant, we just pick up a factor of x on the left-hand side and a constant of integration. So we have nu times 2 lambda minus gamma times x plus C1 is equal to UEL squared. Okay. Okay. From our boundary conditions, we know that UE at x equals 0 is 0, which means that C1 must be 0, right? So we can solve this thing for Lx. So we have L of x is equal to nu over UE 2 lambda minus gamma times x, and this whole thing square root. Um, hmm. Let me go back to my definition of UE, 1 second. Did we find L of x for, oh yes, okay, so I'm going to reference this solution. From the Blasius equation. Okay, so where we had an expression for L of X. Um, so. And then I'm gonna kind of rearrange this so that that is a little more straightforward. So recall from the Laplacius solution, we had that Lx is equal to some constant b times the square root of nu x over u infinity. All right, so we have some consistency with that result too. All right, so since b is generally equal to 1, this implies that first of all, UE is a constant, which is equal to U infinity, and gamma is equal to 0, and lambda is equal to 1/2. In which case we will get back the exact same thing. Okay. Okay. So this is L. Now we want to find UX or UE of X. What we will do is we will divide equation star star by equation star. Okay. So we have, where did equation star star go? I'm just going to copy this so I can read it off the other page easier. Okay. So we have nu lambda divided by gamma nu is equal to L squared U E prime plus U E L prime L divided by L squared U E prime. Now I can delete that. Okay. And this gives us lambda over gamma is equal to 1 plus UEL prime divided by UE prime L. Okay. Okay. I'm going to rearrange this just a tad. So I am going to divide through by UE prime, or multiply through by UE prime over UE. So I have UE prime over UE, lambda over gamma minus 1 is equal to L prime over L. I can also write this as lambda minus gamma over gamma is L prime over L, and then I'm going to solve this so I have just UE prime over UE on the left-hand side. So this is gamma over lambda minus gamma, L prime over L. Um, I want to rearrange how I have this just a tiny bit. So I'm going to move this here. And then essentially what we're going to do is we're going to, shoot, not that. I want to solve these two equations side by side. So I'll write this one. So it's L prime over L is UE prime over UE times lambda minus gamma over gamma. Okay. And then I'm going to separate variables and integrate both of these equations. Okay. Okay. So what I have is natural log of L of X is equal to natural log of UE of X. And then I still have this factor out front. Uh, plus a constant. Okay. And on this side, I also get that we have natural log of UE is equal to gamma over lambda minus gamma times the natural log of L of X plus a constant. Okay. And so I am going to rewrite this as natural log of L of X is equal to natural log of UE of X raised to the lambda minus gamma over gamma power plus a constant. And then I'm going to exponentiate both sides. And I get that L of X is equal to some other constant coefficient out front times UE of X raised to the lambda minus gamma over gamma power. All right, which means that UE of X is equal to 1 over K times, actually, I'm going to call this leading coefficient. What letter do you want for a different constant coefficient?
Yeah.
Beta. Beta times L of X to the gamma over lambda minus gamma. Did you say interesting choice? What's wrong with beta?
Nothing.
I
That's
honestly,
just not the first thing that would come to mind.
I was thinking about substituting all the lambdas and gammas with beta, just to stop writing them all the time. In my head, like 3 steps ago,
Wait. What were you gonna substitute?
the, the gamma and.
Like the gamma over lambda minus gamma?
Yeah, I was thinking about substituting it with beta, so I have to keep writing them in my own
But
notes.
it's so fun to say
So
lambda
beta
over, or gamma over lambda minus gamma, isn't it?
I'm not the one talking.
It's a mouthful. So it turns out like either way you solve this equation from the left hand side or the right hand side, you get the same result. But yeah, now you know that. Do you want to see this one go too? It's a little more straightforward. So if we exponentiate, oh wait, hang on, I gotta move that exponent up. So I have natural log of UE is equal to natural log of L of X raised to the gamma over lambda minus gamma. Plus C1, and then exponentiate. And we get UE of X is equal to beta times L of X gamma over lambda minus gamma. They're the same, yay.
It doesn't look like any other symbol.
It's true. Neither does XC.
C,
XC. This one?
Yeah. That one is horrible to draw and it never looks right.
I know. Even that's not very good. I don't know.
It's not
It's
possible.
like
beta's easy.
you almost did it done with the E, but then you may change your mind. So you're like, "Oh,
Or maybe I just like passed out for a second.
We're trying to draw the answer.
Someone check on me. The and symbol, the ampersand,
No, I'm trying to, I don't know.
that guy?
Not that one, the other one. The birthday draw, it looks kind of like, yeah, like that.
You don't like that one?
I've never seen that one before. It just looks like that.
What, this one? Oh, the XC looks like that.
Yeah,
Yeah, it kind of does.
that's what I was,
I don't know.
well, that could be like the little plot, but, it's not the little plot. There's another one. That looks, it's got a swoop on top and then kind of goes into an S at the bottom.
I don't like that."
Okay.
Oh, now I'm curious. It's a Greek letter?
Yeah, I used it different when I tried to blow it.
And it wasn't this? Oh, is
Maybe
there
it's a-
this one?
Yeah, it's kind of like that.
Oh,
It's
what's
not
the name of
S.
that one? Yeah. It's,
And then there's like delta
Yeah.
too, where they draw a weird delta. It's not
That-
delta, is it?
that's lowercase delta.
Then there's
This
that.
is big delta.
Yeah. beta is my
Omega,
favorite.
omega.
It
Okay.
is my favorite.
Beta's nice. Lambda's my favorite Greek letter. It's so cute. Look at it. Oh, look at it.
I think it's one of those first Greek letters you get introduced to and kind of like lambdas.
I loved lambda.
Upside down font.
Gammas are fun too.
Gammas are nice, yeah, except for I kept wanting to write Y. Did you see me keep doing that? And I'm like, nope. My hand was like, I don't have muscle memory for this. I have muscle memory for Y. Surely that's what you meant. Okay. All right, so now what I'm gonna do is I'm gonna substitute in my expression that we already derived for L of X. Which is L of X is equal to square root 2 lambda minus gamma times the square root of nu x over u infinity. All right, so that means that we have UE of X is equal to beta times the square root of 2 lambda minus gamma square root of nu x over u infinity raised to the gamma over lambda minus gamma. Oh, wait. Oh, yeah, and reminder, this is a constant. Okay. And then I can rearrange this so that I have. Is that terrible? No, it's not bad. I have everything except for the X. I'm gonna separate out. And all of that stuff is also a constant. So I'm gonna think of another letter for a generic constant.
Keeping, did you use alpha?
I was gonna say, you're not gonna say alpha.
Oh, yeah.
Talk.
Why? I liked your beta contribution.
He was laughing.
I
did
Not given.
It's always with.
It was not with, I heard her, I could hear what she's saying and it made me feel very, very sad.
Do we have to have a mediation, you guys?
Listen, I didn't say your first was bad.
Single driven.
It was surprising.
You know, what was just yours?
Good. I didn't have an idea.
Well, we're going with alpha now.
Gamma alpha.
Hi.
That one I will hate.
Times the square root of x. Actually, no, I'm gonna make the square root in a 1/2 in the exponent. So we have x to the gamma over 2 times lambda minus gamma. We could also think of this as UE of x is equal to some constant c times x to the m. So it is a power law.
So we, oh, right, square root. I was like, what did you?
The 1/2. Yeah. So this is a power law where m is equal to gamma over 2 times the quantity lambda minus gamma, which is a constant. There are some irregularities in here.
Get into this beta.
I don't even, no, they didn't use beta, but, huh?
Losers.
Now you're on my team.
I didn't make a mistake with these exponents, right? Like this all looks fine, yes?
Yeah, I
I think they just dropped the parentheses around the lambda minus gamma is what's happened. Okay. Now, let's talk about some specific cases. Okay, so some special cases. Okay, so if we have flow over a wedge, this is when lambda is equal to 1. And flow over a wedge is just like how it sounds. So essentially we have our wedge. And then we have incoming flow like so. And our boundary layer will look like this. And like this. And so we end up with boundary layer like that, kind of. All right, so oh no, now a beta has been introduced.
We got rid of it, remember?
Did we?
Yeah.
We put it inside of alphas.
You probably
They don't want
mark
it
it
to.
in different color. Just to be like different kinds, something.
Why would you do that?
Just make the debate
No,
taxi.
I swear.
That'd be. That'd be something.
It's funny. Just make it capital.
All the three letters are there, Marines.
Sigh.
There's a moment.
This is very sparse. Okay. So in this case, we have UE of X is equal to CXM, where M is equal to 1/2 times 1 minus gamma. So I just let lambda equals 1, obviously. And oh, sorry, this is in okay, so the notes say that this can be rewritten as like gamma over 2 minus gamma, but I don't see how. Does anybody see a way in which that's possible? I don't think so.
How do we bring it out there?
Yeah, I don't know. Without ending up with a square in the numerator
Yeah.
or denominator somehow. I think that this is not right. Okay, I might have to follow up on that. I don't know how that happened, but this is okay. Huh?
I'll plot it and see if something happens.
Okay. Um,
No, it's-
wait, you have what on speed dial?
that's not-
What's that?
It's a graphic. template.
Oh, really? Like on your phone? No.
They're not the same.
Yeah, I didn't think so.
Yeah, so like I plotted both of them next to each other, so they're just not. same.
No, not at all. Not at all the same.
Guys.
Yeah, they're close.
Yes.
Ish.
As my dad says, that only counts in horseshoes and hand grenades.
That's hilarious.
My dad's a fun guy. Little dark, that joke. Okay. In the case where we let how could this be? Everything after this depends on this, and it doesn't make sense. Hang on. Let's go back. Hang on. Let's go back. Let's return to this. So here, this is like a little aside. There was a step that was done where, why in the world would you do that? Well, for reasons unknown to me, after this, there was a step that looks like UE to the 1 plus gamma over 2 lambda minus gamma is equal to alpha times X to the gamma over 2 lambda minus gamma, but you can't do that.
Why did you just bring that on nowhere?
I mean, like, here to here is correct.
Is U infinity supposed to be UE? And not be moved into alpha?
It's written as U infinity.
Huh.
It was written as UE earlier.
But then we said UE had to be U infinity, right?
Mhm.
Somewhere here. Yeah, right here.
Well, that wasn't just for the case of trying to get it to equal Velocius.
Yeah, because I think if it was UE, that would work out instead of infinity.
Yeah, it would.
Oh, okay. Maybe that is the problem in the notes then.
You sure it's equal to U infinity though? Because would that just be to show that the velocity, that was.
Yeah,
just-
yeah, I think it should be UE. I think you're right. I think it should be UE. Yeah, go team. Good job. Actually, let me, so
I'll
this
just
is
accept that change. Be okay with that.
the U infinity?
Yeah.
You should have interrupted me and been like, what do you mean?
I want to be like Lee and just catch it 3 steps ahead of when it reveal.
You didn't want to have any spoilers? Okay, so,
Catch it, chat.
no, he's here. I think he's here. Lee, are you here? Show yourself. Oh, maybe he's not.
No.
He was here earlier, wasn't he?
Yeah, he was talking before. Let me check.
Then where'd you go?
He's not here. Oh, I'm leaving that in the recording for sure. Okay. Everybody turned off the lights and put the like lights on their phones. Okay. I'm gonna let me just move this like this is a constant thing up here. This is a constant. Okay, and then, all right, so we have UE of X is equal to beta times square root of 2 lambda minus gamma quantity times nu. And then we have UE to the minus gamma over 2 lambda minus gamma, right? Yes, I think that's right. And then times X to the gamma 2 lambda minus gamma. So then if I group the UEs,
Get back to UE again. Oh, I got that.
oh, sorry, yes. So back here, wait, where was it? Back here,
Mhm.
this is our definition of L of X. Is this guy.
Right.
And I substituted in UE, I accidentally substituted in this, but that's just for the Blasius solution.
Oh,
Does that make sense? So that was my bad. However, the notes were a little confusing that I was looking at, so. Okay. So we have 1 plus gamma over 2 times lambda minus gamma is equal to, and now this is alpha. Alpha times X to the gamma over 2 lambda minus gamma. Okay, so we have UE to the 2 lambda minus gamma plus gamma over 2 lambda minus gamma, which is equal to alpha X to the gamma minus 2 quantity lambda minus gamma. Can I write this? And then this is UE to the 2 lambda minus gamma divided by 2 quantity lambda minus gamma. Right? Yes. Right-hand side stays the same. And then I need to smoosh this. Okay, so then we have UE is equal to alpha. Well, it's actually kind of a new constant now.
Is this how they're gonna get that random, the other exponent?
Yeah, so I'm gonna like make it just UE to the 1 power and I'll move the exponent over, right? I need another constant.
It's curve, you. Use a chart.
You know that. I'm in charge of judging them.
How about epsilon?
That's great.
Epsilon x to the gamma over 2 quantity lambda minus gamma times 2 gamma minus lambda divided by 2 lambda minus gamma. Yes. And then these cancel. And then this doesn't just look like a typo that forgot the parentheses. You see the confusion here, right? Okay. There. It's not good page management. I'm sorry. There. Okay. So now this is okay. And here, well, for reasons that I don't know, we're letting beta equal gamma. I don't know why we wouldn't just keep it as gamma, but
What if I wanna replace it with gamma later on somewhere else?
actually, I kind of want to just keep it as gamma, to be honest. I don't know why. Like, why? I would do this. Okay, so now if gamma is equal to 0, then m is equal to 0. And this is plain stagnation flow. So that is this. Gamma equals 1. That's this guy that we've done before. If we have, oh, okay, 2. If we have gamma equals 0,
Is gamma
Wait.
equal-
this is, hang on, this is 1.
well,
Wait, what?
why do you say gamma is equal to 1 and 0? On the plane stagnation flow?
Oh, this should be. Oh, wait, yeah, gosh, sorry. 1 and 1. Sorry about that. Okay, if gamma equals 0, and that means that m is equal to 0. This gives us. I'm losing it, you guys. I'm losing it.
Today's the day.
Today is the day.
I'm like, 5 minutes.
Okay, this means that UE of x is equal to some constant times x to the 0, which is just a constant. This is our flat plate Gaussian solution. Okay. if beta is equal to minus 0.1988.
Yeah, hey there.
Oh my God, this is killing me, you guys. It's killing me.
Almost there. Almost there.
Barely. Then that means that pi over 2 gamma is 17 minus 17.9 degrees. This is separation flow. Separation flow. Which looks like this, where this is our 17.9 degrees. So our flow comes in like this, and then we end up with our boundary layer down here. Like so.
Is 17.9 like some critical angle?
Yes, we. Okay, if gamma is between minus 0.1988 and 0, which means that M is between negative 0.0904 and 0. This is corner flow. This is flow around an expansion corner. Which is an adverse pressure gradient situation, adverse pressure gradient. And then the flow ends up decelerated in this circumstance. Okay. Case number 5 is when gamma is between 0 and 2, which means that M is between 0 and infinity. And this is flow against a wedge of half angle. So the angle is pi over 2 gamma. Almost did it. I did do it. So this is flow over a wedge where this angle is pi over 2 times gamma. If gamma goes to minus infinity, that means M goes to -1. This is sink flow, which is like flow around a drain. That. And then last case, if gamma is greater than -2 but less than 0, that means that M is between 1/2 and 0. This is an expansion corner. So this is still pi over 2 times gamma. This is the angle. Oh, wrong way. This way. But now the flow is going like this, I believe. Okay.